Alright, so here we are on our last video for this arithmetic and geometric sequences and functions and translating those two things from one to the other. We just have to cover two more things, and that's discrete and continuous. Now, we've seen discrete and continuous before. We know that discrete's broken up by points, usually like this, and continuous has a continuous, if you will, a continuous line that doesn't have any breaks or jumps. Well, in mathematics, there are some ways that we want to write these functions and represent them with equations. So for discrete functions, things that are broken up by points, we generally write them with our explicit formulas. Okay? That's the a sub n equals, and then whatever it may be. In this case, it's exponential, so I have the geometric formula here. And then we would just substitute our first term in our common ratio and call it good. And the reason why we use sequences to represent discrete is because our inputs, our domain values, are all going to be integers. Because it's going to have your zero spot, your initial amount, your first spot, your first term, your second term, your third term. There's no such thing as, like for instance right here, if I draw this arrow, this would be our first term, this would be our second term. But there's no term in between the first and second term. There's not a 1.5, there's a break there. And so this is why using sequences is so great, because sequences only have first term, second term, third term, your zero term, whatever. There's no 1.5 term. It's kind of like running a race. There's first place, second place, third place, but there is no 1.05 place or any fraction or any decimal place. Okay, that's where we actually use function notation, and that's where continuous functions come into play. If you have a line that has no breaks, we use function notation, and what that kind of implies is that x can be any number you can think of. Whether it's a whole number or an integer, positive, negative, but also decimals and fractions, which is why we said that the domain can be any number between negative infinity and infinity. That's all real numbers. So, and that's how we write it out for a continuous. Here's this slide in a nutshell. Discrete functions get written as explicit equations, like so. Continuous functions get written as function notation, like so. Okay? I'll show you. Look at our first example here. So here I see that I have what kind of function?
Linear.
It's linear, and it's also discrete or continuous?
Continuous.
This is continuous because it has no breaks and no jumps in it. So how am I going to write this? Well, if you rewind the video and go look at the last slide, continuous is written as function notation, right? And because this is linear, that means it's arithmetic, and we write those as dx plus a sub 0. That's your difference in your initial amount. And those are actually really easy to find. We like to show it by just drawing a few points from the graph. And so this point right here would be like 0, 1. This would be 1, 3. And then right here would be 2, 1, 2, 3, 4, 5. So 2, 5, and so on and so forth. And you could take all of these ordered pairs, put them in a table, and then you can actually find what's going on here. How do we get from 1 to 3 and from 3 to 5? Well, we're adding 2 each time, aren't we? Now, is that a common difference or a common ratio? Well, it should be a common difference because we already decided that it's linear and that it's arithmetic. And so we have our common difference, but what's the initial amount? The initial amount is 1. So we have that f of x equals d, which we said is 2x, and then our initial amount, which is, remember this is a sub 0, is 1. And so I'm done. That's all I'd have to do. And that shows two things. It's a function. Therefore, if I didn't even have my graph, it tells me that it's continuous. I also see that it's in the dx plus a sub 0 form, so I know it's arithmetic. I can see the common difference and the initial amount really quickly. But here's something really cool about this. Let me erase this for a second. Is you also remember a while back that we had something called y equals mx plus b, right? Where you have your slope and your y-intercept. Well, your y-intercept is 1, and your slope is rise 2, run 1, which gave us a slope of 2. Right? And you'll notice that these two forms are very similar. Well, they're actually the exact same thing. The common difference is the same thing as slope. The initial amount is the same thing as the y-intercept. It's always been that way, and that's how these two things are all related. Anyway, cool. Why don't you try the next one?
All right, really quickly. Hey, on that last one, I just wanted to remind you that even though this is a function and it's continuous, we use basically the explicit formula version to find the answer. We had to find those points in order to get it. So even though it's continuous, we find the point. So here's another one. Right off the bat, I asked the question, is this a linear function or an exponential function? You're like, oh, this is linear because it forms a straight line. I can kind of see it. So I know it's going to be linear, but is it continuous or discrete? Well, I don't see a line here, I just see dots, so I know this is discrete. And if it's discrete, it means we're using explicit formulas. Specifically for linear, all linear equations are arithmetic. And so that means this is the formula that we want to end up with. Because we only want the whole number of values. We don't want to know what 1.5 is. We just want to know what 1 is, what 2 is, what 3 is, and those terms of the sequence. So in order to fill this out, I'm going to need to know two things. I need to know what a sub 1 equals, and I need to know what the common difference is. And again, I could do it from the graph, but we're going to go ahead and make a table. I think tables are fantastic. And since we know this is a straight line, we don't have to pick every value. We just pick a couple values. I can see, for instance, at -1, I go up 4. So at -1, I have a 4, right? At 0, I have a 1. By the way, that shouldn't be a y, huh? We should call that f of x. We should get in the habit of f of x really means y. And then at 1, I go down -2. And I could keep going, but I think the pattern is the same. So all I have to do now is they're sequential. They're -1, 0, 1 in order. This is getting bigger or smaller. Looks like it's getting smaller, and that's okay because look at this. If we do the slope sum, positive, negative, this line is going in a negative direction, so it should be minus. So 4 minus 1 is 3. Or 4 to 1 is -3, excuse me. 1 to -2 is -3. So I have a common difference of -3. And I found the first term. The first term is that a sub 1 is going to be -2. I have those two things. Now I can substitute them back into the equation. A sub n equals the first term, which is going to be -2, plus the difference, which is plus a -3. We're just going to put -3 times n minus 1. And now I can find any term on that sequence. Cool. Here's another one. Boom. Oh my gosh. Kind of hard to see maybe for you. It might help if I put the line there. This doesn't have a line, but if you could see the line looks like that. And that would mean this is exponential. Exponential means that it is going to be something to either geometric or an exponential function. But before we go any further, we have to ask the question, is this continuous or discrete? Well, again, this has dots, so it's discrete. If it's discrete, it's exponential, but we call that geometric. Exponential graphs are geometric. If it was continuous, it would just be the function, but this is going to be the geometric formula, which is a sub n equals a sub 1 times the rate to the n minus 1. And we put it in parentheses because we do that for students because when you substitute into your calculator, it just makes it so you don't make any mistakes. You don't have to have the parentheses, it's just useful for the calculator. And now, I need two things. I need the first term, and I need the ratio. And so to do that, again, I can look and kind of figure it out, but I can also just make a table. And so I'll just pick at -1, I can't see what that is. At -1, I don't know what that is, but I might figure it out later. It looks like it's less than 1, but I don't know. But I know at 1, it's 0. Excuse me, let's switch that around. What I have to say is at 0, it's 1. When x is 0, it's 1. That was a test, you passed. At 1, it goes up 1, 2, 3, so it's a 3. And at 2, it goes up 1, 2, 3, 4, 5, 6, 7, 8, 9. 9! So, now I see, okay, this looks like I can do this, but I already know it's exponential, so I know I'm not looking for a common difference. I'm looking for a ratio. This ratio looks like it's going to be getting bigger, so that means I'm multiplying. 1 times what will give me 3? Oh, I think if I multiply it by 3, I can get to 3. And if I multiply 3 times 3, that should give me to 9. Now let's see if that works. To go the opposite direction, I'd have to divide. So 9 divided by 3 would give me 3. 3 divided by 3 would give me 1. What's 1 divided by 3? That would give me 1/3. And that looks about right. That's where that's at. So I think we got this right. We know what the ratio is. The ratio is 3. And now what is my first term? My first term is where x was 1, or I could look in the graph here. And that's a 3. And now I just have to substitute it into the equation. So I take my equation, I say a sub n, and what's my first term? It's 3. What's my rate? It's 3. And it's to the n minus 1. So I've written this equation, I just need to find 2 pieces of information. It's all about memorization. All right, Mr. Nelson, show us how it's done.
Show us how it's
done. Show us what you're working with.
Right. Oh man, looks like this one's decreasing. So let's get a table made really quick. I'm going to just shift this over. I'm going to shift this over this way a little bit. I'm going to make a table just to see this. I see that it's already exponential, which means it's going to be geometric. Now I just need to figure out whether I need to do the function or if I need to do the explicit formula. But because this is continuous, and it has no gaps in it, no breaks, it's continuous, I'm going to use the function notation for this. And the function notation for geometric or exponential equations is going to be a sub 0 times r to the power of x. So I do need the initial amount, and I need the common ratio. So I'm going to make a table of some of the points. Again, around 0, I think it's a great idea to go even to the negative side because those ones look like it's really easy to read. So I'm going to go from -3 to -2 to -1 to 0, even up to 1. Even, maybe we can calculate that first term too. So let's go ahead and grab some of these points from the graph. At -3, we're at 1, 2, 3, 4, 5, 6, 7, 8. At -2, we're at 1, 2, 3, 4. At -1, we're at 2. At 0, we are at 1. And it's really hard to tell where this one's at, so we're going to see if we can fill in that blank by using that pattern. We already know it's geometric, so we know it's a common ratio and that we should be multiplying to get to the next term. But we are decreasing. And because this is decreasing, I know that I'm going to be multiplying by a fraction. But what might help us is to figure out what we're dividing by and then do 1 over that. To get from 8 to 4, to divide, we'd have to divide by 2. 8 divided by 2, sorry, is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. And 1 divided by 2 would be 1/2. But it's not what you divide by, right? Common ratio is always what you multiply by. And so dividing by 2 is the same thing as multiplying by 1/2. And so here we have a common ratio of 1/2. 8 times 1/2 is 4. 4 times 1/2 is 2. 2 times 1/2 is 1. 1 times 1/2 is 1/2. So we have our common ratio. We've got this part. And we also have our initial amount. This is our a sub 0. And so now we just need to substitute into our function. So f of x equals our initial amount, which is 1, times our common ratio, which we see here is 1/2, to the power of x, and that's the function I would like to see. Now the question is, do I need the 1 there? No, I don't need the 1, but it's okay to put it there. Okay, it could just be 1/2 to the power of x, because anything with a coefficient of 1 you don't usually have to write. So if you didn't put the 1 there, that's okay.
You're awesome, Mr. Nelson. That was the question I was going to ask. Do I need the 1? But you don't need the 1, but it's okay to have it there. All right. So again, you don't have to be able to see it, so I'm going to kind of draw the lines so you can kind of see it. That is definitely not linear. That means it looks like it's going to be exponential. It looks like as I go from left to right that it's going to be bigger, so it's going to be increasing. So this is going to be exponential, but before I go any further with this exponential, I need to ask, is it continuous or discrete? Well, there's dots, so it's discrete. If it's discrete, that means that we're going with an explicit equation. The explicit for exponential equations is geometric. Geometric is a sub n equals a sub 1 times the rate to the n minus 1. And again, you don't have to put it in parentheses. I just do because I think about my calculator. And so I'm going to need the first term. I'll bring that down a little lower. And I'm going to need the, ooh, that's a horrible looking R. For my ratio, right? So I need to find those two things. Again, the best way I can do that is to make a table. And so I go x and f of x. Remember, f of x is the same as y. That's your y values. But we're going to call it f of x. And now, I'm going to have to pick some points. These all look hard to figure out, so I'll just put one of them just to see if I can, when I figure it out, does it look like I got the point there? I'm going to go 0, 1, 2, and maybe up to 3, just to make sure. And so I'll go ahead and plug in the values. For -1, I don't know what that is. I'm going to put a question mark there for right now and get back to it. Then I go to the next one. I say when it's 0, it's 1. Cool, I can deal with that. When it's 1, it goes up 1, 2, 3, 4. I get to 4. When I go to 2, I get 1, 2, 3, 4, 5, 16. Okay, I'll just say it's 16. And 3, oh, I can't go to 3. Why? Because my 3 isn't even on the graph. That means it's definitely getting big fast. So I could probably figure it out if I wanted to. It's not on my graph, but let's see. It's exponential, which means it's growth. Exponential means I have a rate. It means I'm multiplying. What am I multiplying 1 by to get to 4? I think it's 4. Let's check. Is 4 times 4 16? It is. What is 16 times 4?
64.
64. So that's why it wasn't on my graph, because my graph goes up to 16, and I need to go to 64, which would be somewhere on the top of the building. So, on the other way, to go, if I'm going times to go this way, I have to divide to go the other way, or multiply by 1/4. So 4 times 1/4 is 1, and 1 times 1/4 is, this should be 1/4. And I look, that looks about 1/4. Not perfect, but I think that'll work. I think we got it right. So, now I know my rate is 4, and I know my first term is 4. And now all I have to do is just substitute it in. A sub n equals my first term, which we now know is 4, times the rate, which we now know is 4, to the power of n minus 1. I have written the geometric formula for this exponential problem. That should help you. If you have any other questions, please email us. Get the work done. Let's take a test.